Welcome. In the world of quantitative finance, there's this high-stakes game being played every single nanosecond. It's a world where machine learning promises to unlock untold riches, but honestly, it more often delivers catastrophic failure to anyone who's unprepared. Today, we're not just going to pull back the curtain. Oh no, we are giving you the complete architectural blueprint to avoid the 7 deadly pitfalls that doom the vast majority of financial ML projects.
Look, this isn't just an opinion. This is a battle-scarred observation from Marcos López de Prado, a true pioneer in this field. The graveyard of ML-based hedge funds is just vast, and it's growing every day. They show up armed with these brilliant algorithms, petabytes of data, and dreams of a 4.0 Sharpe ratio, only to get completely wiped out by the market's brutal reality. And the question is, why? What are they all getting wrong? Okay, I have to jump in here. This is exactly my situation. I've been grinding away, building models, and my latest backtest just came back with a Sharpe ratio of 4.0. I mean, that's legendary, right? It feels like I've finally cracked the code. But after hearing you say that, I have this sinking feeling. Is it real, or is it a complete illusion?
That is the single most important question in this entire business. And I promise you, by the end of this explainer, you will have a definitive, mathematical answer. We're going to start our journey in the quants graveyard, rebuild from the ground up with proper data foundations, seal the data contamination leaks that poison most backtests, and finally, we'll confront the great overfitting illusion. Only then can we design the quant factory of 2026. Okay, let's dive into this.
So our first stop is the quants graveyard, the final resting place of countless brilliant strategies. And the tombstone for most of them is carved with the first and most fundamental pitfall, what we call the Sisyphus Paradigm. And this isn't a flaw in your code. It's a catastrophic flaw in the research structure itself.
You see, investment firms love the silo model for discretionary traders. It prevents them from groupthink, protects diversification, it makes sense. But applying this same logic to quants, it's a recipe for absolute disaster. They hire 50 brilliant PhDs, lock them in 50 virtual silos, and then command each one to invent a unique, profitable strategy from scratch. It's a futile, soul-crushing labor. Just like Sisyphus, cursed to push a boulder up a hill for eternity, only to watch it roll right back down.
So you've got two roads here. The silo on the left forces quants into this lonely, frantic search. And what's worse, with today's supercomputing power, it just accelerates the failure. Each PhD can now run 1 million backtests instead of 1,000, which massively amplifies the risk of finding a false positive. And hey, if they do find something, chances are the other 49 PhDs found the exact same crowded trade. The only model that actually works is on the right, the meta-strategy paradigm. Think of it like a modern car factory. You have specialists for data processing, feature engineering, modeling, backtesting, and portfolio construction. It's an assembly line for discovering alpha. Okay, so let's say you've built the factory. It's totally useless if the raw materials you feed into it are corrupted. And this brings us to the next 3 pitfalls, which contaminate the very source code of your strategy, the data itself. Get this part wrong, and your entire factory will only produce lemons. Wait a second, this seems like it should be the easy part. For data, why can't we just feed the ML model the raw price history of a stock? I mean, isn't that the purest signal we have? That's an excellent and critical question, which leads us straight into pitfall number 2. The problem is this fundamental conflict at the heart of time series analysis. Most statistical tools, most ML models, they require a stationary series, one where properties like the mean and variance are constant over time. But prices, well, they trend, they're non-stationary. The standard fix is to compute returns, the period over period change. This makes the series stationary, but in doing so, you erase almost all of its memory. And memory is the very thing your model needs to find predictive patterns. And this chart just illustrates the tragedy perfectly. The green line is the price series. It has trends, it has character, it has memory. Now look at that blue line. Those are the integer differentiated returns. Yeah, it's stationary, but it's been reduced to high-frequency noise. All the valuable, low-frequency information is gone. You've essentially thrown the predicted baby out with the statistical bathwater.
So how do we escape this dilemma? Well, the answer is an elegant piece of mathematics called fractional differentiation, or FracDiff. Instead of taking the first difference and destroying all memory, we use calculus to find the minimum amount of differentiation, a fractional amount, needed to just barely achieve stationarity. This lets us preserve the maximum possible memory for our models. It is the true Goldilocks solution. Not too much, not too little, just right.
Okay, let's move to pitfall number 3, sampling on the wrong clock. Nearly everyone samples data based on time, every minute, hour, or day. But information doesn't arrive on a fixed schedule. Look at this chart. The black line, sampling every tick or trade, is incredibly erratic. Time bars aren't much better, but when you sample based on market activity, like whenever $1 million is traded, that's the blue dollar bars, you get a much more stable, well-behaved series. You are sampling at the speed of information, not the speed of a clock. And this allows you to compute powerful microstructure features, like VPEN, which can measure order flow toxicity and warn of a potential flash crash. You can't see that in a daily bar.
Okay, that's a huge insight. So we've got clean, fractionally differentiated, activity-sampled data. Now we have to tell the model what we want it to predict. We have to label the events. Is it as simple as, if the price is higher in 5 days, we label it a buy, and if it's lower, a sell?
You've just perfectly described pitfall number 4, the fixed time horizon fallacy. That method is deeply flawed. Think about it. A 2% move on a quiet day is a massive signal, but on a volatile day, it's just noise. Worse, it ignores how trading actually works. No serious trader just holds a position for 10 days regardless of what happens. They use profit targets and stop losses. And that's exactly what the triple barrier method shown here does. We define 3 barriers for every position. An upper barrier for profit taking, a lower one for cutting losses, and a vertical time limit. The label is determined by which barrier gets touched first. This teaches the model the path-dependent reality of managing risk and returns.
We are making real progress. We've built our factory, we've secured our raw materials, but now we enter a far more subtle and dangerous territory: data contamination. This is where your model secretly learns from information it shouldn't have, leading to backtests that look like pure genius, but fail instantly in live trading.
This analogy just nails pitfall number 5. In finance, our data points aren't independent, like in many classic ML problems. The outcome of a position we label today depends on prices over the next week. The outcome of a position we label tomorrow depends on prices in its next week. They overlap. It's like every sample is contaminated by the ones that came before it. This concurrency makes it incredibly difficult for a model to learn true causality, because the information from different events is all just smeared together.
Now, this contamination becomes an absolute catastrophe during model validation. That's pitfall number 6. If you just use the standard k-fold cross-validation from a library like scikit-learn, you are guaranteeing failure. It shuffles the data, which means information from the future will leak from your training set into your test set. Your model will look clairvoyant. The fix requires a specialized process. First, we purge. We identify every single training label whose outcome window overlaps with our test period, and we delete them. Second, we apply an embargo. We also remove a small slice of training data after the test set to prevent information leaking backwards due to serial correlation.
And this chart makes it crystal clear. You see the test set in blue. The purging process removes the training data in the red overlap period just before it. Then, the embargo creates another buffer zone right after the test set. These two no-fly zones are non-negotiable. They ensure your model is being tested on truly independent, unseen data, giving you an honest assessment of its actual predictive power.
And now, we arrive at the final pitfall. The mother of all sins. The one that has vaporized more capital and destroyed more quant careers than all the others combined. Backtest overfitting. This is the demon that separates a genuine discovery from a statistical mirage.
Look very closely at this. This is arguably the most important plot in modern finance. On the horizontal axis is the number of backtests you run. On the vertical axis is the maximum Sharpe ratio you should expect to find from all those tests, purely by chance, assuming the true strategy has a Sharpe of 0. Look at the dashed line. If you run 1,000 trials on a supercomputer, which is nothing these days, you should expect to find a strategy with a Sharpe ratio over 3, from pure, dumb luck.
Oh no, I definitely ran more than 1,000 trials. I tweaked features, adjusted parameters, I tried different lookback windows, and my best result, the one I was so proud of, was that 4.0 Sharpe. Exactly. You asked if your 4.0 Sharpe was real or fake. According to this plot, if you leverage modern supercomputing to run enough random tests, a result of 4.0 isn't just possible, it's statistically inevitable. This is selection bias under multiple testing, and it is the beating heart of the overfitting illusion. So how do we ever trust a backtest again? We need a more powerful weapon. This is the deflated Sharpe ratio, or DSR. Think of it as a lie detector for backtests.
It takes your beautiful inflated Sharpe ratio and systematically deflates it by accounting for all the sources of luck, the number of tests you ran, the skew and kurtosis of your returns, and the length of your backtest. What it gives you back is the probability that your finding is a true positive. Wow. So you feed it your amazing backtest, and it tells you the cold, hard probability that you're just fooling yourself. My mind is kind of blown right now.
Precisely. It is the moment of truth. And now that we've navigated all 7 pitfalls, let's put everything together. Let's build the blueprint for the quant factory of the future, a process engineered from the ground up to produce robust, verifiable strategies and to avoid these deadly traps.
This new paradigm, it revolutionizes everything. Look at this table. The old way to hire a portfolio manager is to be impressed by their high Sharpe ratio. The quant factory approach uses the DSR to calculate the probability their entire track record is a false positive. The old way is to treat strategies like static assets. The new way is to monitor their evolution in real time. And the output isn't one strategy, it's a meta-strategy of many small decorrelated alphas that are combined intelligently using robust techniques like hierarchical risk parity, or HRP, which understands the deep hierarchical structure of your signals, not some fragile covariance matrix that will betray you in a crisis.
Now, we've covered a huge amount of ground today. All of these concepts, FracDiff, the triple barrier, Purged cross-validation, the DSR, HRP, are detailed with mathematical rigor in this foundational book, Advances in Financial Machine Learning by Dr. López de Prado. For anyone who is truly serious about this field, this is your Bible.
So it all comes down to this. All the advanced math, the code, the supercomputers, it's all completely worthless if the underlying research process is broken. That's the crucial point. The tools of machine learning are immensely powerful, but financial markets are a uniquely treacherous landscape designed to fool you. Lasting success isn't about a lone genius finding one magic algorithm. It's about building an industrial-grade, collaborative process designed to systematically separate truth from statistical illusion. So the final question for you, and for everyone listening, is this. Are you pushing a boulder up a hill, alone, forever? Or are you building a quant factory,